So basically, I want to spend the hour today introducing the SEPIO framework. We've talked a lot about it. We've seen a few examples of how it might be applied. Just because a lot of the driver projects are familiar with this and many of them are using it or exploring it already, we've kind of gone into this with the assumption that we're at least going to test this as a first pass at our evidence model and see how it works to support our needs. And again, from our initial analyses, it seems like it's very well aligned with our requirements and the way that we're thinking about evidence and provenance information. So for today, I want to just give a little bit of background and context for the evidence modeling work, since it's been a while since we chatted about this, and we've kind of spottily done some work around evidence requirements and analysis over the past year or two. And now we're going to spend several weeks a focused effort, I think, on this. So I want to start out with just a little bit of background and context for this work, and then I'll spend most of the meeting running through these slides, giving an overview of the SEPIO model and framework. And at the end, take a little bit of a look at what it might look like to apply this to the VA work. And then I'm not going to get too deep into the modeling aspects today, and then keep that more at a high level. And then next week, we can take a deeper dive into kind of the structure and the semantics of the SEPIO model itself in more granular detail, and how it represents evidence and provenance information. Starting way back at the beginning, of course, we had a mandate set out in our initial roadmap to support evidence and provenance information, and said we would also try to do this in a way that supports standards around evidence and provenance curation, such as the ACMG guidelines. And of course, we want to support this in our V0 release that we're working towards now. And as we can see in the bottom here, this is really the last big area that we need to tackle. We're effectively done, I think, with most of these other areas, or we've decided to defer them. And again, this is a work that we've been doing over the last several weeks, is kind of rounding out and closing the loop on some of these issues in these other areas. So the evidence and provenance is the main thing that we still have to do. Now, we've, as I said, done quite a bit of work here already in this space, on and off over the last year or so. So I think we're starting off in a good place to make some fast progress and at least get some a decent straw man together to put out with the V0 release. We spent a lot of time extracting some initial considerations from the data example catalog that we put together early on, and thinking about evidence and provenance requirements based on those examples. We developed a set of evidence and provenance competency questions for each of the core statement types that we're focusing on that were quite informative. And I started a document to synthesize the modeling requirements based on the data examples and the competency questions and other discussions, which we'll take a quick look at later. And of course, we've also started to explore and play with some existing standards that might support our work. So we have a good basis to jump off from here. And I think, the take home at a very high level from what we've done so far is that across the different variant annotation types and sources that we have in our purview, we're really faced with very diverse types of evidence, quite variable requirements for the detail and precision around which evidence and provenance metadata are modeled, and also very many different use cases for which this evidence and provenance information may be applied. So there's some challenges here, but I think the SEPIO framework and the people that we have on this team are well suited to address those. So these modeling challenges must, of course, be considered alongside factors that we've identified as important for adoption and development of the VA-Spec. We've had these discussions over the past couple months, and we all know that a standard isn't going to get used if it's not expressive enough to capture all the detail and nuance that's required for some use cases. But it also won't get adopted if it imposes too complex or rich a structure for the simpler use cases, which are often more common and just as important. So we know we'll need to balance flexibility with extensibility, but ultimately our priority here is to support interoperability. And this is, again, the key challenge with any type of standards development work, where you're trying to support very diverse sources of data and allow them to be aggregated and operated on together. So we also, realize that to keep pace with what the community needs and to leverage the expertise and resources in the community of users, we should try to allow for some framework for distributed development of models for any type of annotation. So we talked about the idea that gene and sequence annotation use cases have come our way, and we don't necessarily have the bandwidth to support those in a kind of centralized development model. So we should think about ways to allow the community to bring their needs to the table, to develop strawman models under a framework and bring those to the group, so that all development doesn't kind of have a bottleneck around a small core group of developers. And of course, we realized that one way to support all this, again, is with this idea of grounding the specification in a shared foundational model that can be adapted to address the specific needs of particular data sources or use cases and different variant annotation types. So all of these kind of insights and realizations are behind our recent shift towards providing the VA-Spec as an extensible modeling framework that will support this type of community-driven development, flexible adoption and development of models that are fit to the data that it's meant to support. So as a reminder, these are just the components that we've laid out for this framework. It'll be based around a generic domain and format agnostic model for representing annotations really of any type as structured data objects. And this will provide the conceptual and logical foundation on which extensions and schema can be built to support specific annotation types and use cases. So we'll have to also provide extension mechanisms and support in the form of modeling constructs and technical guidance to support this customization and specialization of the generic model. And again, this is going to be critical to allow community-driven development and testing of models. And I think the key thing that we will provide, it's a bit more concrete and immediately useful, will be a set of GA4GH implementation guides. And these will provide concrete models and formal message specifications for specific variant annotation types. So we've already identified 7 or 8 that we're going to target initially. And these will provide the GA4GH community with a recommended standard for out-of-the-box interoperability if they choose to adopt them, and also provide an example of how to apply the framework to create new models should the community need new models. And then, of course, on the technical side, we'll want to provide some reference implementation, a library of software and services that can demonstrate and be used to create compliant data. So feel free to interrupt if there's questions or comments on this. Again, just trying to kind of recap and get everyone back on the same page after our break. Any questions about that before I start talking about SEPIO? Okay. So the SEPIO modeling framework. SEPIO stands for the Scientific Evidence and Provenance Information Ontology. And the goal, I think, for today is just for me to provide a general understanding of the model and the framework, how it's has been developed, how it can be applied, and again, not go too deep into the modeling details, save some of that for next week. So SEPIO basically provides a modeling framework for representing scientific assertions and the evidence and the provenance that support them. It was first developed as an ontology, hence the name, by the Monarch Initiative to support the standard representation of evidence and provenance that was pulling from various genotype-phenotype databases and data sets. So it was integrating all this data from model organism databases and human databases about genotype-phenotype associations and related data types. They all had very different types and models for representing evidence and provenance. And Monarch was trying to aggregate these all into a single kind of RDF linked data graph. So an ontology made the most sense at that stage for kind of defining classes and relationships and patterns that could be used to standardize the representation of evidence and provenance. But as we thought more broadly and started to see other applications for a framework like this, the initial ontology model has been abstracted into a generic information model that can be implemented really in any language or format. And this ontological component has kind of become optional. If you want to have ontological support, you can use the ontology to structure your data or map your data elements. But really, it's this generic information model now that can be implemented in any language or format that fits your needs. So this core information model, again, is domain agnostic. It's meant to be able to represent assertions and their evidence and provenance of any kind. And when you want to apply SEPIO to a specific data set or use case, you need to define what we call a profile, which is essentially a kind of specialized schema that extends or customizes the core model for a specific domain, data type, or application. And again, this should sound very familiar to the framework that we laid out for VA. So before diving into the framework itself, I just want to highlight that SEPIO is already being used or explored by many different projects in many different areas, including several GA4GH driver projects. So again, the most mature implementations really are in the Monarch initiative, which I just talked about. ClinGen as well has developed and is deploying 4 different SEPIO profiles for different types of clinical interpretations of genes and variants. And groups like Civic and the VIC are exploring and testing SEPIO for representing somatic variant interpretations. The BRCA Exchange has a couple grant proposals in for applying SEPIO to represent its BRCA gene variant annotation data. The HL7 clinical genomics information model is exploring using SEPIO to represent patient-level genomic data, and the NCATS data translator and BioLink models, which are a bit more outside of our purview, are exploring using SEPIO for more graph-based representations of evidence and provenance for, again, integrating very diverse biomedical knowledge. So again, the key take-home here is you know, we already see this being used and applied in a lot of the driver projects inside of our work. So it comes with some validation that it may be useful for us in defining our specification. So again, what started as this kind of simple ontology has evolved into a modeling framework. We call the SEPIO modeling framework to allow its broad application to really any type of assertion, scientific assertion, data or use case. And the foundation of this framework is this flexible information model. Again, it's domain agnostic, has generic concepts that are capable of representing any type of assertion and evidence behind it. The profiling mechanism then allows implementations to extend this core model with domain and application specific content to create, again, these SEPIO profiles. These are essentially these custom schema that specialize SEPIO for particular application. And we'll walk through some examples of how this works in a few minutes. And then, as I said, the framework also provides as a third component this ontological representation of the model, which, if desired, can be used to produce linked data with ontology-based semantics. But again, this is a completely optional component of the framework. I'm not going to talk about it much today because it's not something that is particularly critical for us at this stage, but ultimately it's there if we end up supporting JSON schema and want to create JSON LD. We can do that quite simply by mapping our modeling constructs to classes and properties in the SEPIO ontology, and then basically get some RDF for free out of that. So I'm going to be focusing mostly on reviewing what the core information model looks like, and then talking about profiling mechanisms and how you specialize that for specific applications. So to start, I want to explain the structure and the semantics of this core information model at a more conceptual level. So we can all understand what type of data it can represent and how. And this slide shows how the core axis of the model, shown on the right, mirrors 3 universal tasks that are involved in making any evidence-based assertion. These tasks are defined in the center column, and then the diagram on the left here shows examples of each task in the context of an ACMG-based variant interpretation workflow. It seemed an apt example to use for our community. So if we start at the bottom here, we can follow how we build up from data into knowledge. Step one is data curation. This is the retrieval and organization of data that might be used as evidence for a target proposition. A proposition is basically what we call the possible fact that evidence is curated and evaluated against. And if that evidence is sufficient, then that proposition is ultimately put forth as true in an assertion. So the proposition here that in our example, evidence is being curated towards is that this BRCA2 variant is pathogenic for breast cancer. So curators here may collect things like population frequency data or functional data for a variant because it's relevant for evaluating the truth of this proposition here. And each of the distinct data objects or data points that we see over on the left here is what SEPIO would call an evidence item. So step two then is evidence interpretation. This is really the cognitive task of evaluating and grouping these evidence items into discrete arguments and weighing the strength and direction of support that those arguments provide for our target proposition. So in our example, the process of evaluating evidence would involve grouping and evaluating all the population frequency data together as one argument. The functional data becomes another argument, again, according to the ACMG framework, which provides formal criteria that prescribe exactly how to do this. And these discrete arguments are interpreted to make what SEPIO calls evidence lines. We'll go a little bit more detail about exactly what these are and how they're used in a couple minutes. So then the final step in this kind of universal workflow is knowledge creation. And this is the collective assessment of all of these evidence lines in order to draw a final conclusion, which can be expressed as an assertion. So in our example, there are three such evidence lines or arguments that would be collectively assessed according to the ACMG rules in this case, and to determine if collectively they warrant the assertion that BRCA2, this BRCA2 variant is indeed pathogenic for breast cancer. So in this example, of course, the ACMG guidelines provide a formal reasoning framework for doing all of this, for organizing and weighting and collectively evaluating evidence. But these three tasks really happen anytime an evidence-based assertion is made, even if it's only informally in the mind of a curator or a scientist. These three basic tasks, I think, are kind of universally performed in order to generate knowledge-based assertions. So the key take-home here is that, again, these three classes that comprise the core axis of SEPIO on the right really map to and represent the outputs of these three universal tasks that are involved in making evidence-based assertions. And this tight coupling and association will be important for thinking about how the model can be applied in practice to real data. So again, please interrupt if there's any questions or comments. I'm going to keep going, but chime in if you have anything to say. So I want to dig a little bit deeper into the meaning and the utility of each of these core classes, starting with assertions. So we define an assertion as any statement of purported truth is made by a particular agent on a particular occasion. There are some examples of different types of assertions that we might come across on the right. Of course, the variant pathogenicity interpretations are a type of assertion that we just saw in the last example. Variant drug response predictions, assertions about gene expression, assertions about the biological function of genes. Obviously there's a myriad of different types of assertions that might be made, but these are just a few examples of types of knowledge and evidence-based assertions that are in scope for our work. A few characteristics of assertions. One is that they have truth value. Again, they put forth a proposition that may or may not be true, and our belief in an assertion ultimately rests on the evidence and the provenance that support it. Scientific assertions that we're concerned about are inherently evidence-based. They result from logical inference and conclusion based on the interpretation of evidence. And finally, a bit about the identity criteria for assertions. The identity of an assertion really depends on what it claims to be true, but also who is asserting it and when that assertion is made. So there can be many different assertions made by different agents or on different occasions that all put forth the same proposition is true. And there's a good example of this if you look at ClinVar, and we can see this ClinVar RCV record that has 4 different SCVs grouped under it. Each of these put forth the same underlying proposition that this particular variant is pathogenic for breast cancer, but they represent distinct assertion instances as they're all made by different agents and on different occasions.
Matt, just quick technical note. So in the previous screen, you had the BRAF listed for colorectal cancer. So that's probably not a very good example because it is the case in vitro, but it's not the case in vivo.
Sorry, it's the case where? I didn't catch that.
So in cell lines, colorectal cell lines, you can see sensitivity to BRAF. However, for patient, that doesn't work.
Okay, so that particular example there,
yes,
you don't think just from your personal knowledge applies in patients?
It's not really a good example.
Okay, good to know. Let me just make a quick note of that. Pen here. All right, I'll make a note and I'll choose a different example then. All right, so moving on to evidence lines. Again, these are discrete independent arguments that are relevant to the validity of an assertion. Evidence lines represent the interpretation of one or more pieces of information as arguments for or against a particular proposition that's being evaluated. So these arguments have direction, how they can support or dispute that proposition, and they're also evaluated to have a certain strength or weight to them. You know, in ACMG, we see terms like strong or moderate or weak or supporting. And these characteristics are all evaluated relative to a particular proposition that they're being evaluated against. So for example, you know, allele counts and frequency calculations from various exact populations may be collectively assessed to provide one argument that is deemed to have moderate strength supporting the pathogenicity of the variant for breast cancer. And it's important to realize here that the same data, same evidence items here can be interpreted as providing a different direction or different strength of evidence when they're evaluated by different agents or when they're evaluated against different propositions. We see some examples of this on the right. So the same population frequency data may be interpreted by one curator as providing strong evidence of the variant's pathogenicity for breast cancer, but a different curator might come along and interpret them to have only provide moderate evidence of pathogenicity. So there's variability in how the same data can be interpreted as evidence, and this evidence line object is where we can attach that information to separate objects in the data to capture how different curators might interpret the same evidence in different ways. And then another example is that this same population frequency data might quite rightly be interpreted to support the variant's pathogenicity for one disease, disease 1 in this case, but actually dispute its pathogenicity or be kind of negative evidence for a second disease that might be more highly penetrant, such that the frequency actually supports a benign interpretation. So again, the same underlying data about the frequency of a variant can be interpreted differently as evidence depending on who is doing the interpretation or the proposition that it is really being interpreted toward. So again, these are just some of the nuances that really exist in the world of evaluating and interpreting evidence that the core structure of SEPIO is really built to support. You know, if a specific application needs to get down to that level of granularity and detail, SEPIO has the structures to support that. So again, with these evidence lines, though, in practice, they're not always useful, they're not always needed. They're needed when a data provider wants to capture this nuanced detail about how data is specifically interpreted as evidence. So if they want to organized collections of evidence items that all contribute to one argument and represent this idea of combinatorial evidence, then this evidence item object can be used to group those, or evidence line object can be used to group those together. Or if a particular application, again, wants to capture the strength or direction of support that the evidence is interpreted to provide, then the evidence line class here becomes useful. But many use cases won't have this type of requirement, and in that case, we can skip over this evidence line and create simpler models using SEPIO based on some shortcut relations I'll show in a minute. So just another key thing to keep in mind here about evidence lines is that they're available, but they don't need to be used. And in cases of simpler data, we can kind of skip over them to create a model that matches the complexity of the data. So finally, evidence items, they represent these individual pieces of information that are used to build up an evidence line. Really, any type of information can serve as evidence, but this information only becomes an evidence item when it realizes this role, when it's interpreted or laid out as evidence. So, for example, a piece of population frequency data, again, going back to the same example, really only becomes an evidence item once it's assessed to evaluate something like a variant's pathogenicity. So SEPIO defines several high-level categories of information entities that are most commonly used or referenced as evidence. So if we look under the information entity class in SEPIO, again, parenthetically, these can be evidence items anytime the information entity is applied as evidence. But ultimately, these are all types of information entities. And we define these different classes representing information at different levels of granularity or aggregation or extraction that are often referenced as evidence in the data that we've come across. And this is everything from atomic data items to specific records in a database or full data sets, figures or tables and publications. Prior assertions can be referenced as evidence. Documents and publications are often referenced because they hold evidence or provenance information. And then we have this notion of a study finding object, which is kind of an artifact that lets you pull together the findings about a particular subject from one study into a structured object to just provide a more efficient way of representing that. And we'll see examples of that in a minute. But these are the basic structures that we provide, and instances of these classes can be created anytime a data provider wants to structure the information about these discrete pieces of information that are used as evidence. And again, this covers the vast majority of use cases that we've come across. So maybe next week we can go into more detail about what these look like under the hood. But for now, I just wanted to kind of show what they are. There's a table here that kind of defines them and gives examples just for reference. But again, we can go into more detail with respect to modeling of these next week. So moving on to structures for representing provenance. Again, in blue here is this central axis of the SEPIO model, the three classes that we just talked about. And surrounding these concepts are concepts that let us describe how and when and by whom these core artifacts are created. This can include contributions made to them by different agents, activities that these agents perform in making these contributions, any resources that they use in doing so, methods that specify how activities like making an assertion or interpreting evidence are performed. There's a method class for that, and of course documents that might describe all of these things. So the structure here, as you can see, allows very fine-grained tracking of provenance at the level of the assertion or at the level of its supporting evidence lines and evidence items. So we'll dive deeper again into the modeling details of this next week. But for today, I just wanted to give this higher level sense of the fact that we have these classes that can help represent provenance in a very detailed and fine-grained way about any of these artifacts, any of these processes that are involved in making evidence-based assertions. So a few final slides about the model itself that really are about the various ways that SEPIO can be flexible and the flexibility that it affords. So I think the core model that we just saw is actually relatively simple. There's a few classes, a few relationships, but it's really the flexibility and extensibility of this that allows SEPIO to represent either very simple or very rich and complex use cases. These core classes can be used as building blocks to create complex structures and rich data structures that can be very quite expansive in their breadth, particularly in cases where there are multiple lines of evidence supporting an assertion or multiple evidence items that contribute to a given evidence line. We can see that you can end up with data structures that are quite broad, and we see examples in the ACMG, for example, where there are very many evidence lines that might support a given assertion. So the cardinality here in the central axis, where assertions can have multiple evidence lines and evidence lines can have multiple evidence items, can allow the creation of these very broad and rich evidence structures. And then SEPIO structures can also go very deep in cases where prior assertions are used as evidence, and the evidence and provenance for those assertions is also captured. So in this case here, we may have several levels of evidence, what we call them, where again, the evidence item supporting your root assertion here may be a prior assertion, and then you can use the same evidence structure here to represent the evidence and provenance behind that assertion, and ultimately end up with these provenance trails of arbitrary depth, depending on how many assertions you're tracing back over in time. So again, combining these two dimensions of kind of extensibility, you can end up with some very rich and complex structures that are both broad and deep in nature. And we'll see some examples of this as well. So the final thing to talk about here is the shortcut relations that SEPIO provides, which can be used to directly link objects that are normally connected via multiple edges in the model, in a fully normalized model, and to more directly connect them. And this supports these more concise representations of data when sparser evidence and provenance are available. So there's a couple examples here. Instead of going from assertion through an evidence line or item to a publication, for example, that describes that evidence, if this information isn't available in a data source, you can link directly from an assertion and say that this assertion has evidence from source, some particular publication. Similarly, the example I used before, where if you don't really have enough information to know what the different lines of evidence or arguments are, all you have is some pieces of information that were used as evidence. You can skip over this evidence line object and just directly connect the assertion to information that is used as evidence to support it. So again, the take home here, I think, from these last few slides is that these different shortcut relations and the arbitrary kind of expansions in breadth and depth that you can do with SEPIO allow implementations to define a model at a level of complexity that matches their data or their use case. So you can end up with very simple models for sparse evidence and provenance data and very complex models when that metadata is rich. This is here just more for reference. This is a full view of the core information model as kind of a UML-like class diagram. It shows again, the different core classes and classes for representing evidence and provenance, the various attributes and data types that those take. And this model, again, it's domain agnostic, and it specifies all the ways and different terms and design patterns in the ontology or in the model that might be used to structure data. And this is really the starting point from which implementations can derive a custom schema through the profiling process. And that's what we're going to go through next after I run through a quick data example using Civic. So again, I thought it might be useful to see a little more concrete of an example about how we can represent real data using SEPIO. And I'm going to do this using a Civic assertion, mainly because their curation workflow and their data model is conceptually very closely aligned with that of SEPIO. They distinguish these same notions of assertions and evidence lines and evidence items in their curation workflow in their model. And one type of assertion that they curate, of course, are predictive associations between a variant and a response to treatment with a particular drug. And the example we'll look at here is the assertion that this specific EGFR variant is or predicts sensitivity to non-small cell lung carcinoma of that disease to the drug afatinib. So here are the basic steps in the curation workflow. And if Alex is on the call, he can correct me if I misstate here, but as I understand it, essentially curators find and review and summarize findings from reports of clinical trials that are relevant to the particular proposition that they're looking at. Again, in this case, if they're looking at this particular variant with this particular disease and this particular drug, then they'll find publications or other reports reporting the outcomes of trials that tested this combination of entities together. So they will simply find and review and summarize those findings according to the civic curation guidelines, and then they will evaluate the strength and the direction of evidence that a particular finding or study provides with respect to the target proposition that they're looking at here. So again, this first task really is generating what SEPIO would call an evidence item. The second task, where they're interpreting the evidence provided by that evidence item for a particular proposition, generates what we would call an evidence line. And then the final step is, if an abundance of evidence exists to support this particular proposition, say there's multiple studies that are providing strong evidence supporting it, then civic curators create an assertion record that states their belief that this proposition here has enough evidence and that it is likely true. And of course, this is aligned with the SEPIO assertion idea. So this is the civic interface showing this assertion record, just so we can see what type of data points and structures civic collects about the assertion and about the evidence and provenance that support it. So outlined in red are the elements that structure the semantics of the assertion itself. And again, when I say assertion here, I'm really talking about in VA what we call statements, these kind of knowledge level assertions of fact about a variant. So we see that they structure elements such as the variant itself, the drug that is being used to treat the disease, and the disease here, as well as codified representation of the clinical significance outcome of expressed in that assertion. And the provenance of the assertion that they capture includes contributing curators, shown up here, and the assertion method that is being used in part to make this assertion. So also then in the interface below, we see in orange 6 different lines of evidence here that support the assertion. Each of these is based on a different published study. And the details of one of these evidence lines is kind of blown up here on the right to show the strength of the evidence line. It's the level B. There's a 5-tier ABCDE, I think, system that Civic uses. And also the direction of that evidence, if it supports or disputes the proposition of the assertion here. And here we see that this evidence is supporting this particular proposition. The details of the study finding itself that represent the underlying evidence item here are shown in green. This includes a free text description of the data from the study. At present, Civic doesn't really structure the underlying evidence items, the underlying data from the study. It's mostly captured in a free text statement here. And then they capture the source publication and some readout or assessment of the quality of the data itself, which it calls the evidence rating. So how does SEPIO represent this information? Here's the high-level structure of a model that would support it, where each element in the civic data that we just saw is kind of listed at the level next to the SEPIO construct that would capture that information. So at the assertion level, SEPIO would, of course, support capturing the structurative semantics of the claim, just as we do in the VA model. It's patterned very much around the same idea in SEPIO of having a subject and a predicate and an object, along with qualifiers that can really refine and specify in detail the meaning of that statement in a computable way. And then we also would hang the contributor contributions and the A&P category indicating the strength of assertion from this assertion object in SEPIO. The evidence lines in SEPIO here, again, just 3 of the 6 are shown for space reasons, but here is where we would, of course, hang the strength and direction that are the evidence is interpreted to have for this particular assertion. And then we represent the underlying evidence data as study findings. Again, you recall the different structures that we define to represent types of information that can be used as evidence. Here, the study finding structure is a good match, and it essentially bundles the data and provenance information related to a specific finding from a study. So the finding object here is where we might hang the free text description of the finding, the publication it was sourced from, and the kind of trust or evidence rating about really the quality of that data. And then finally, you know, I've included a slide that holds a fully fleshed out data example, just more for reference. This shows how the actual data from this assertion record would be structured using the SEPIO model. And again, I'm not going to walk through this, but it's, I think, high res enough if you want to zoom in after the call and really get into the details of the different attributes and elements in the SEPIO model and how they capture the different data points from this civic record. And I'll just qualify this by saying that maybe slightly out of date. There's still some evolution in kind of the names of some of these SEPIO elements, but it should be largely up to date. So I'll pause here for a second before going into the profiling process and just see if people have any questions or comments so far.
I was going to say, Matt, this is fantastic, but I just want to make sure we're in line with what the goal is here again. So the idea here is that when we get through this, we're going to try to stand this up as sort of a reference framework for what we're doing in VA and align it to meet that. Or again, could you just remind me from the beginning what the end game here is? Yeah,
I'll get to that in just probably 5 or 6 minutes. Let me run through this profiling.
Okay, all right.
Yeah, I realize it's getting on here in time, but that's why I set apart a couple weeks for this, because I want to just make sure that everyone is on the same page before we start this, and I'll definitely get to that, Larry. So the SEPIO profiling process here has 5 basic steps. Again, recall that applying SEPIO to a particular use case or data set requires specializing the core generic model to create one of these profiles, and these are the 5 steps in creating one of these profiles that we'll walk through. And I'll use an example here from our VA work, the molecular consequence statement type. So I'm gonna just hop out real fast here and just remind people some of the requirements that we collected for evidence and provenance around this molecular consequence statement type. So based on the competency questions, based on our looking at data examples, this is kind of the evidence and provenance synthesis document here. You know, these are the core elements in the statement itself. With respect to provenance, you know, we wanted to capture the agent who is authoring the assertion itself, which is typically some software tool, you know, what type of agent that is. If it's a tool, what the version is, what the algorithms, if it implements a specific algorithm, you know, the date that the annotation was made. In respect to evidence, you know, really it is this genomic feature annotation data set that is the primary kind of piece of evidence that goes into this process of generating these molecular consequence annotations. And we identified several characteristics that we wanted to capture of that, you know, what its name or ID is, what version of the data set, who created it, when they created it, what the source is, these types of things. And then there's also the information about the reference genome build that was used as well in generating that data set. So those are the basic requirements that we have bring to this process here. And step one is really to then figure out what core classes in the SEPIO model you need to be able to represent that information. And essentially that involves taking your data elements or your requirements, mapping those to the SEPIO classes that would structure them, as we see in the table here, and then that points you to the classes in SEPIO that you actually need to represent that information. So this table just maps all of those requirements that I just laid out to the SEPIO class that would be needed to represent that, and those are shown in blue. In this case, this small subset of core classes is all that's really needed to represent this relatively simple use case. Much simpler than the civic example, much simpler than the ACMG pathogenicity interpretation example I can show next. So once you've done that, then we need to think about defining specializations of those classes, where you need to create subtypes or instances of these core concepts to represent domain-specific concepts. So in this case, our generic core classes like assertion or data set can be specialized to represent the domain-specific concepts for our use case. In this case, a molecular consequence statement is really a subtype of an assertion, and this notion of a genomic feature annotation data set is a subtype of a data set. And of course, if you need to represent domain entities that your assertion is about, that's another need that you would need to consider as well. Step three is then building the structure of the model itself using the classes that you identified as building blocks. Just stitch them together into a structure that matches the source data and requirements that you have for your application. So again, in our case, it's a very simple substructure. It's all that's needed to represent the requirements that we had for molecular consequence. And again, this is just a straw man. It assumes that we don't need to represent the reference genome as a discrete separate object. It assumes that we use the kind of more direct contribution model as opposed to the qualified contribution model, which is something we'll have to get back into later. So I just tried to make this as simple as possible, just to show the other end of the spectrum here of how simple these models can be. So once you've done that, then it's just a matter of looking at the core SEPIO classes and picking the attributes that you need for your use case. So out of everything that you have in an assertion, the ones in green, I think, are the ones that we would need for a molecular consequence statement. In this case, we are also kind of specializing this assertion here so that we can apply these specific constraints to the values of these different attributes. But this becomes our kind of model for a molecular consequence statement that is SEPIO based but matches the model that we laid out earlier in our earlier work. And then the final step is to create and bind value sets or data types to these attributes. So if you need value sets, you can ideally leverage existing terminological standards to constrain value entry for a specific attribute. So in the case of the molecular consequence statement, we might want to define a value set for molecular consequence, which is shown here and which we've already done. You might define a value set of different software algorithms or how to capture a genome build. Again, these are questions that are open for discussion that we'll get to hopefully next week when we take a deeper dive into this particular profile. And at the end of the day, you end up with this information model that is your profile for molecular consequences. Again, it really just has the statement itself. It directly links to this data set, which is the evidence, piece of evidence supporting it, which captures the important metadata about that data set. And then the agent in this case is typically a software agent. The software agent class has specific attributes to capture things like version and an algorithm implemented. Again, this is just a straw man, but again, it's kind of to illustrate the process of creating a profile for a particularly simple use case. I do have another example here of a much more complex profile that was created for ACMG-based variant pathogenicity interpretations. It was the first profile defined by ClinGen for their work. I won't go through it other than just to scroll through here and show that this use case required the use of many more of the classes from the SEPIO core model, many more specializations, particularly the different types of evidence items that they needed to define structures for is much richer here. Obviously, the ACMG guidelines are quite detailed and precise, so there's going to be a lot of precision and nuance to capture here. But these are the specializations. The structure itself was multi-tiered, just following the ACMG workflow. It required kind of 2 levels of evidence where you have an intermediate criterion assessment as kind of an intermediate assertion here. So again, the structure can be very complex in this case. You know, the same process of customizing class definitions was performed, and value set creation, many more value sets obviously needed for this case to end up with a final interpretation profile, again, that's much richer than the one that we saw for molecular consequence, but again, still founded and based on the same underlying concepts in the core SEPIO model. Here's a data example from the ClinGen data set. So a real variant interpretation record structured using this. And this is just a side-by-side comparison then of the 3 different profile structures that we've come across, going from the simplest molecular consequence to the most complex pathogenicity interpretation. I'll skip over the ontology support for now. Again, it's not directly applicable to us right now. And for the last 5 minutes, maybe just start to think about how we potentially use and apply this in our work. But I'll pause if there are any questions about that profiling process now. I'll take 1 minute to take any of those questions. Again, I think this is what we're going to work through over the next few weeks. So as we go through these examples together, I think it'll become clear how it works and whether this is a good fit for our requirements. So briefly, SEPIO itself, primary developer is mainly me. There's a lot of input we get from external communities who are using it for other Monarch developers, but it's primarily myself developing this right now. Funding comes from the various projects that are using the model. You know, again, the implementation right now when you define these profiles is primarily through my working directly with collaborators and pilot adopters to help them develop these profiles. You know, the documentation right now is the ontology itself and a GitHub wiki that has some of these diagrams and data dictionaries. But the bottom line is, you know, is the core model begins to harden and the community of use grows around it. What's really needed next is more formal documentation, implementation guidelines, governance and tooling support. You know, it's still in its early stages, but it really needs this hardening and this formalization in order to kind of take it to the next level. And one idea that's come up a few times is that given the contributors and the adopters and the use cases that SEPIO has in common with GKS and VA efforts, there may be an opportunity to align and to co-evolve these standards in a way that benefits both parties. You know, these commonalities, I think, have already resulted in a coordination and a convergence between SEPIO and VA, and potentially formalizing this relationship could increase the synergies that it provides. You know, SEPIO for its part could benefit from the infrastructure GA4GH could provide, from its reputation and credibility, and from the technical expertise of many of its participants to help advance and formalize the SEPIO framework. And then GA4GH efforts, including VA and sequence annotation and others, could benefit from you know, being able to have direct input into shaping SEPIO as it evolves and hardens and ensuring that it meets their modeling requirements and use cases. So again, just wanted to put that out there. It was a bit of an aside, but something that I think deserves some consideration and discussion in the near future. And finally, you know, with respect to how we might start applying this to VA. You know, in my opinion, it is very well suited to address the modeling and implementation challenges that we face in VA. The core models are very well aligned. It provides that flexible framework for extension and customization that we've settled on needing for our work. It's been informed and tested by many of the same driver projects that are driving VA development. So really the next steps would be to start defining profiles for each of the VA statements, much like the one that we just walked through for molecular consequence. So we could start doing this exercise. Again, it's fairly systematic, and I think it should be fairly straightforward. There's always decisions that need to be made and different choices that need to be made, but I think it will be relatively straightforward to start developing some strawman profiles for our 6 different statement types, evaluating how well SEPIO addresses the modeling and implementation requirements we have, potentially providing feedback to SEPIO to make improvements or changes to the model to support our use cases. And then if all seems to pass muster, we can release the VA-Spec as a set of SEPIO-based models or profiles that kind of, again, kind of show how these two standards can work together. And then longer term, identify commonalities among profiles that we define for these 6 types that might let us converge on 1 or 2 different reusable templates that support different levels of complexity. But I think the first step is really just taking these statement types individually and seeing how SEPIO would naturally support them. So Larry, I'm not sure if that answered all of your questions. I think that's kind of where I'm thinking the next step goes and what we will be tackling over the next several weeks, and just kind of go from there. But I know we're at the top of the hour, so if people have comments or questions, I'm happy to stay on for another couple minutes. But again, we'll pick this up next week with a continued presentation.